Hello and welcome back to our channel Physics Safari. I hope you guys are doing good and studying well. So today we are into the sixth lesson on the AMI, sixth video lesson on the AMI. And today's topic is going to be the translational EMF. We're going to talk about the translational EMF. Translational EMF. Now, as the name suggests, this is going to be about the EMF which would be induced because of the motion, and the motion could be linear motion, and going forward we can also come across the rotational motion also. Then we are going to talk about the EMF due to rotational motion. So the two parts over here we have EMF induced due to translational and the rotational. We're going to discuss one by one. All good. Now this part is kind of important. Again, as I told you, this entire topic is important. I'm repeating it again. Well, even this part is a very important segment of that. Okay, so let's quickly start, and let me just show you a couple of situations in which this concept of translational EMF would be appearing to you. A quick recap: the Faraday says there are going to be EMF induced if and only if the flux linked with that closed loop is a function of time, and the Lenz's says that the direction of induced EMF, hence the direction of the induced current, should be in such a way that it is going to oppose the cause of it. Now cause could be motion, cause could be change in the magnetic field, so the cause could be anything, but whatever is the cause, the induced current is going to oppose that by producing an magnetic field around it in such a way that the cause should be opposed. इतना तो बेसिक अपने को पता है. Also, if you have not seen the previous videos on this EMI, you must go and watch. The link should be provided in the I button as well as in the description box. You will get the complete link of the entire, maybe this videos of the previous topics, as well as all the playlists should be there. Also, don't forget to like, share and subscribe if you are liking the way I teach. All good. And if it is of any advantage to you, अगर आपको थोड़ा सा भी फायदा होता है मेरे क्लासेस से, please like, share and subscribe. All good. So coming to the translational EMF, the first thing which you need to understand is, let's say if I have a rod, if I have a metallic conducting rod. When I say conducting rod, it means I should have the free electrons which is available to be mobile, to move. Now I'm gonna give you one standard diagram. So the standard diagram says, let's say it is moving towards right with a velocity v, and the magnetic field is present inwards in the inward direction, and it's constant magnetic field. Okay, it's a constant magnetic field. Let's say this is magnetic field B, and it is moving with the velocity v in the right side direction. Already in the very first video I have discussed how the electrons will be affected by the magnetic as well as the electric field, and how we get the saturation state, after which the movement of the electron stops and we have a steady current, that is called saturation current also, or steady state में हम लोग को वो मिलता है. Over here what happened, due to this movement towards right in this magnetic field, the electron over here will start moving in this direction, and hence this will be a positive in nature and this would be negative in nature. ये हमने already discuss कर लिया था. इसको, this one I'm going to take as a standard diagram, और standard diagram आप इसको लेके चलो, और standard condition आप मान कर चलो कि भैया this is your standard condition. After this whatever happens could be read, could be understood, could be taken as a variation in this. हम उसी को आपको समझाने का कोशिश कर रहे हैं. अच्छी बात है. Now we know that the flux is all about B dot A, right? So the flux change could be achieved by changing the magnetic field or by changing the area of the loop linked in that magnetic field. So the magnetic field I can change the area, and the area change, it's not like I'm going to change the length of this, I'm going to change the width of this. Area which it is going to swipe in that magnetic field, exactly what I mean to say by the area change. It's not like that if I have my favorite this duster and I'm making it move in the magnetic field, it does not mean that this area is going to change. Of course not. The area in which the magnetic lines of field changes, for example, let's suppose in this region I have the magnetic field and I'm entering this Just in this region. So you can see that now the moment I cross this barrier, it will start interacting with the magnetic field, and the area which is interacting with the magnetic field, that would change, my dear. All good? तो जितना एरिया मैग्नेटिक फील्ड के इंटरेक्शंस में हो और वो चेंज करता है, that's exactly what I want to say by the this A. If I have a closed loop, I'm going to talk about this in later on. I'm going to discuss with you about the impact of the change in the area, but as of now you need to understand the flux change could be achieved by changing the magnetic field or the change in the area or the both. If I change both of it, still the flux will be changing and EMF would be induced. Okay, so the first thing which I can do is, let's say case number 1, I'm going to change the velocity opposite. Now, my dear students, the velocity of this rod is now, let's suppose, in this direction, keeping the magnetic field same inward. Now, what's going to be the polarity? That's the question. Look, I'm just going to explain you this one, and rest I'm going to just tell you the tricks how to memorize, remember that. Okay, when I'm going to explain this to you, this is going to be a good revision recap for you as well. Let us suppose if I have a positive charge over here and it is moving in this direction. This rod is moving in this direction. So the velocity of the charge is this way and the magnetic field is inside, which means if I look at the force that would be acting on this charge, my dear, will be downward. Direction of velocity, aapke 4 fingers or all your 4 fingers should be in the direction of the velocity of the conductor, and you should curl that towards inside, and over here inside is the direction of magnetic field. So you need to curl your fingers in the direction of magnetic field. Then the direction in which your thumb is pointing is going to be the direction of the force on this positive charge. So here we have ting, it's going to be downward, right? It means the positive charge is going to move towards this side, and here we're going to have the accumulation of the positive charge, which means this side, my dear, is going to be positive, having the positive polarity, which means this has to be the negative polarity. So what could you see over here? From the standard diagram, the polarity has changed because I have changed one parameter. I have changed change in velocity direction, change in the velocity. And I'm only talking about the direction, my dear, okay? So the moment I changed one of the parameters out of these 2 parameters, you can see the polarity has taken a turn. Polarity has become opposite from the standard diagram. All good? Okay, likewise, let's say I'm only changing the magnetic field. Change the magnetic field. Change the magnetic field. Change the magnetic field. Okay, now the change in magnetic field I can do from the standard diagram, or I can also do from here also. I'm doing with the standard diagram. In the standard diagram, the magnetic field is inside and the velocity is rightward. I'm going to use the same thing. You can see that it's still, I'm going to keep the velocity rightward, and this time, my dear, the magnetic field I'm taking outside the plane. Magnetic field I'm taking outside the plane. See what's going to happen. Velocity and the magnetic field is outward. So take like this. You can see still my thumb is pointing downward. It means this side will have the positive polarity and this side we're going to have the negative polarity, which is exactly similar to this. So if I change the parameter for once from this standard condition, I'm going to have change in the polarity for once. Now whatever we had in the standard diagram is going to be reversed from there. All good? Now let us say that, guys, I'm changing from here. I'm having the velocity in this direction. You can just memorize this way. If I have the velocity in this direction. All good? And now the magnetic field is also outward. So there is a change in the magnetic field. See what's going to happen. Velocity is this direction. Magnetic field is outward. It means I must put all my 4 fingers in the direction of velocity. Curl the finger. Thumb is pointing upward. Which means the polarity is going to be positive on the top side of it. So we're going to have a positive polarity, my dear. And here we're going to have the negative polarity. So what can we conclude? If I change the parameter for once, either that could be a velocity or that could be a magnetic field, the polarity would take one change. It will be reversed. So you can see, what is the difference in these 2 situations? The only difference what we have is a change in the magnetic field. It was down inside, now it's outside. See the change in the polarity. If I do it again, for instance, this time, I'm going to change the velocity also. See what's going to happen. If I change the velocity in this direction, and yes, the magnetic field is outside the plane, check out the polarity. So velocity is in this direction, field is outward like this, ting ting, the force is going to be downward. So the polarity, you can see downward is going to be positive and top is going to be negative. Well, it is back to the same thing, right? So if you do the changes for the 2 times, the polarity would be regained. Or वापस से same polarity would come. 1 change, polarity would change. 2 change, polarity would be reversed. वापस से वही आ जाएगा. तो आपको ट्रिक्स दिमाग में होनी चाहिए कि अगर किसी ने दे रखा है कि भैया this is a standard diagram, ये आपके दिमाग में होना चाहिए. Velocity rightward and the magnetic field inside, and you can do the comparison with this. Now let's, for example, if I give you a certain question that, okay, dear student, let's say I give you something like this. Okay, here we have a conducting rod and its velocity is in this direction and the magnetic field is inside. Well, I believe it's already on the board. Chalo koi nahi, that's okay. You have this situation. Moment you see this one, these diagrams are not given to you. So only thing which you know in your mind, that standard diagram looks like this one. What is the difference in this? B is same, the velocity is reversed. It means the polarity which was positive on the top should be negative now, because we have just changed one parameter. Now let's say, again, one more example. Let's suppose you have been given this question. Velocity is in this direction and the polarity of the, in the direction of magnetic field is outside the plane, and there's nothing given. Only this one is given and you have this in your mind. This already you know in your mind. Well, what are the differences? Velocity changed. Velocity is changed over here. You can see that. It means plus is no more here. It should be minus. So just for consideration, you can write minus over here. The magnetic field is also changed from here. It means this minus should be changed to plus. It means it will retain what it had as in the very beginning. It should retain that. So this should be very, very clear to you how we can easily figure out the polarity if the magnetic field and the direction of velocity is given, and if it is changing also, you will be able to do it quite easily. But just make sure that you do remember this standard diagram. All good? Chalo. Now let us move on towards certain problems. So when we talk about the translational EMF, let us have an example, बच्चों. एक छोटा सा example आपको समझ में आना चाहिए. Let us say that if I have a magnetic field existing, let's suppose like this. There is a magnetic field, and here we have tick 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 tick, and let's suppose like this. I have a square loop. I have a square loop, or like this, like this, and this is moving in this towards this with a velocity v. At time t is equals to 0, it is here completely outside this magnetic field, but after a certain time, let's say half of it is outside the magnetic field and half of it is inside the magnetic field and still moving with the velocity v. And in some time later, it is completely inside the magnetic field, and going forward in some time, half of it or maybe certain part of it is inside the magnetic field and most of it and some part of it is outside and still moving with the same velocity v, you know. So this is a situation, okay. This is the situation what we have. This is a situation that we have over here. आपको दिखाना है कि what would be the direction of induced current in this loop. I'm just giving you the vertices name. Let's say A, B, C and D. So the same thing will be there everywhere. A, B, C, D, anti-clock. Okay. So you have to tell me the direction of, induced current. Direction of induced current. Direction of induced current in the loop, in the closed loop. मैंने इसको closed loop बोल दिया है. आपको इसमें direction of induced current दिखाना है कि and during all these 3 cases, so इसको let us say this is case number 1, case number 2 and the case number 3 बच्चों. In all these 3 different situations, what would be the direction of induced current? All good? So you can pause the video or एक बार try on your own and then we're going to do it together. All good? ठीक है. So I believe you must have paused and tried and now we can do it together. हम लोग इसको साथ में easily कर सकते हैं. All good? ठीक है. देखो. It's easy one. It's not that complicated or difficult. Need to understand. Okay. So when it was outside the magnetic field, there was no linkage of the magnetic field. So the flux over here is going to be 0. There is no nothing. because there is no magnetic field, and flux is B dot A, which is not there. So there is no point of having any flux. So there is, of course, there is no point of having any flux change. Now, when we come to talk about this part, a little bit of part of it is inside the magnetic field. It means a part of it, a portion of it is linked with the magnetic field. A portion of it is linked with the magnetic field. It means we have a flux. Now, the change in the flux is of increasing nature, right? Because initially it was 0, but certainly we'll be having some flux. Let's suppose that is flux 1 over here. It means now the flux has increased. So, guys, change in the flux d phi by dt over here is a positive value more than 1. So the flux is increasing, and that would be the reason for the induced EMF, because we know that induced EMF should be negative of d phi upon dt. And this negative sign indicates that the induced EMF should be in such a way that which would oppose this change. All cool? Now, the magnetic flux is increasing. It means we can have an induced current in this for sure, because the induced EMF is there. Now, the direction of that induced current should be oriented in such a way that should create a magnetic field towards outward. Because why the flux is increasing? Because the magnetic field linked with this area is increasing. Magnetic field आपका increase कर रहा है the moment it enters the magnetic region. All good? So the magnetic field produced by the current induced in this loop should oppose this change, which has the nature of increasing the magnetic field towards inside. तो बाहर की ओर magnetic field produce करना चाहेगा. So definitely I can see that the current in this should be in this direction, for it can create a magnetic field in outward direction. So बच्चों, the magnetic current induced in this is gonna be anti-clockwise. The current in this should flow in this direction, my dear kids. I believe you are okay with that. You have understood this part, right? Okay, now come to the situation 2. The moment it has entered completely, it is completely exposed to the magnetic field. So till it is inside the magnetic field, there is no change in the magnetic flux. And since there is no change in the magnetic flux, which means induced EMF should be 0, that implies the induced current should also be 0. So there will not be any current induced in this loop. So there should not be any induced current. Now let's come to the third case. Over here, what we have is, in this region, in this case, this loop is going out of the field. It means the number of magnetic lines of field which is interacting with this loop is decreasing. So that means the magnetic field linked with this loop is decreasing. And of course, even we have an increase or a decrease of the magnetic field or the linked loop areas, we can have the change in the flux linked. And here the flux is decreasing. Decrease क्यों कर रहा है? The decrease is because of the velocity which is going outward. It means there should be a magnetic induced current which is going to produce a magnetic field in this, which will oppose the decrease of this magnetic field. Let me just repeat one more time. In this case, the magnetic field towards inside the plane is decreasing. So this is a phenomenon. वो इसका decrease होना अपने आप में एक phenomenon है. So the induced current over here will try to oppose this decrease. मतलब कि if it is decreasing towards inside, वो और देगा अंदर की ओर, ले जाओ भाई तुम decrease मत हो, हम तुम्हारे साथ हैं. So the current induced in this should be in such a way that should produce a magnetic field inside the loop, अंदर की ओर, inside the plane, which clearly means that the current in this should be in this direction, and hence this time the direction of induced current is opposite to what we had over here in the very beginning when it was entering the magnetic field. So in this case, the direction of current should be in this direction, clockwise. बच्चों एक clear है? I believe आपको ये बातें समझ में आई होगी कि how the direction of induced current is influenced because of the change in the flux, and that change in the flux could be because of the change in the magnetic field or due to the velocity of the loop, उसका जो area होता है. इस केस में magnetic field is constant, right? But the loop, the area linked with the magnetic field were not same in these three cases. So this is a classic example when how the area change impacts your induced current. In this case, the magnetic field towards inside the plane was constant, remained constant throughout. Only thing which changed, not the area of the loop, that was still the same. If it is A, let's suppose, whatever length it is, it would remain same. The only thing which is going to change is the area linked with the magnetic field. उसमें कितना चेंज आ रहा है वो आपको यहाँ पे दिख रहा था. ठीक है, चलो एक और एग्जांपल करते हैं बच्चों. Let us do one more example. मान लो कि we have a wire of length L, okay, wire of length L, and again same wire of length L bent in this shape, and let's suppose this angle is theta. This angle is theta between these two wires, and this conductor is pulled in this direction with the velocity v. इसको right side में with the velocity v हमने move करा, and this direction of velocity is such a way that it is the midpoint of this, so I can say that बच्चों this is theta by 2, and in fact this is also theta by 2. All good. You have to tell me polarity of the induced EMF. Okay, there is a magnetic field inside the plane. There is a magnetic field towards inside the plane. So you have to tell me the polarity of induced EMF. Polarity of induced EMF. Point number 1 and point number 2. Magnitude of the polarity of the EMF. Magnitude of induced EMF. ये दो बातें आपको मुझे बतानी है. You pause the video, try करो. All good? You pause the video, आप इसको try करो. So I believe you guys must have given it a try. आपने इसको try कर लिया होगा. अच्छा, अब चलो साथ में करते हैं, है ना? तो पहली बात तो we need to understand that when we write induced EMF, which I've taught you in the very first video, as I've told you, you should watch that video if you have not seen that video. Induced EMF is given as what? BVL sine of theta, where the theta is the angle between the length vector and the velocity vector. Over here, what we can see, this length and the velocity are not in the same direction. So what we need to do is, we have to figure out that component of the length which is in the direction of the velocity. इसके perpendicular में कौन सा component होगा जी? So obviously this is not perpendicular to this. So let me drop down a perpendicular like this. Now you can see that this length, that this dot red is in the direction perpendicular to this velocity vector. क्योंकि बच्चों in this formula if I say BVL simply, then the length L is taken in the direction perpendicular to the velocity, उसी component को लेते हैं. तो this part is gonna be in the direction perpendicular to the velocity. इसको मैं थोड़ा और extend कर देता हूँ just for your more visibility, है ना? Now, so this part is gonna be perpendicular. तो बच्चों ठीक है, इसका तो easily we can find it out. If it is L, ये कितना आ गया? This is gonna be L sine of theta upon 2. All cool? Likewise, even for this part, so diagram, let me just make it more symmetric. इतना symmetric दिख नहीं रहा, but please understand this is a symmetric diagram, you know. So even this part, बच्चों, has to be L times of sine theta upon 2. All good? Now we can easily understand that here we're going to have an induced EMF, which is value is going to be B, magnetic field B, V, L sine theta by 2. So over here the induced EMF, my dear kids, let's suppose even मान लो in this part, you know, there is going to be B, V, L sine theta upon 2, and here also we'll be having, let's suppose E2, BVL sine theta upon 2. Because of the symmetry, both the EMF are coming out to be equal. So first of all, total EMF induced, the total EMF induced is going to be 2 times of if I'm going to add them. Acha, sir, how could you say that both the EMF are the same? Like remember your current electricity chapter. If I have something like this, we can add it up. But if I have something like this, you know, like this, we cannot just add them up because the polarity is not in the same direction. So before I get into the addition of these two to write 2 times of BVL sin theta upon 2, I must ensure whether the direction of the polarity induced is in same way or opposite way. तो अपने को वो पता होना चाहिए before we just get into the addition of it. Okay, now understand. Remember the standard figure that I've told in the very beginning. Just for your reference, I'm drawing it. वैसे तो ड्रॉ करने की जरूरत नहीं होनी चाहिए. Velocity is V, rightward. Magnetic field is inside. Polarity क्या था बच्चों? प्लस ऊपर, नेगेटिव नीचे. अब इसको आप देख लो. Magnetic field inside, velocity rightward. ऊपर होना चाहिए प्लस, नीचे होना चाहिए नेगेटिव. The same thing should be applicable for this length of the rod. See how the polarity is going to be, which means this has to be a higher polarity. हुयो, ऐसा होना चाहिए. Sorry about that sound. So yeah, I mean like this is how it's gonna be, E1. Now come to this one, same thing. Polarity has to be top. वो दिमाग में होना चाहिए आपको, इसलिए थोड़े से ट्रिक्स, थोड़े से मेमोरीज पावर का बहुत ही जरूरत पड़ता है ना, थोड़ा सा मेमोरी तो बहुत चाहिए होता है ना। तो बच्चों यहाँ पे पोलैरिटी क्या हो जाएगा, सेम थिंग, टिक टिक ना, दिस इज गोना बी योर E2। अब देखो, नाउ दिस रॉड हैज द टू बैटरीज, it could be you can say replaced by the two batteries of EMF E1 and E2 respectively in this orientation, and as you could see it is in the same pattern, it means the net EMF should be addition of E1 and E2। अब इसमें कोई दिक्कत आपको नहीं होनी चाहिए। तो now I'm totally free to add these two EMF, so E total बच्चों that's going to be 2BVL sin थीटा अपॉन 2। ये बहुत ही मजे में हमने कर लिया और आपका जो पोलैरिटी है उसको भी मैंने दिखा दिया। ऑल गुड। अच्छा, दिस ब्रिंग्स अस to a point where we can conclude one thing, that if the body's length is not in the direction perpendicular to the velocity, what we can do, and the second thing, if this element is not very much symmetric or geometrical known figure, तब हम क्या करेंगे उस केस में, वो आपको मैं बताता हूं। उसके लिए हम एक कॉन्सेप्ट यूज करते हैं, L effective length। So write the heading L effective for asymmetrical object for random elements। थोड़ा इसको अब ध्यान से देख लो, बहुत इंपॉर्टेंट है, बहुत इंपॉर्टेंट चीज है ना। लेट्स से फॉर एग्जांपल बच्चों, इट इज अ रॉड, ऐसा कुछ पॉइंट ऐसा कोई रॉड है व्हिच इज लाइक वेरी मच रैंडम इन शेप और कुछ भी ऐसा है, ठीक है। Now this is moving, इसको हटा दो, this marker is now over, it is moving let's say towards right with a velocity v and we have a magnetic field B, well that is inward the plane, obviously ऐसा कुछ है। Now obviously when it is moving in the magnetic field there is going to be change in the flux, will have the EMF induced A is equals to BVL, but the point is let's suppose the length of this curved section, पूरा इसका जो curved एक rod है, इसका पूरा का पूरा length L है बच्चों। Now tell me one thing, is this length perpendicular to the velocity? Is this length perpendicular to the velocity? Is this length perpendicular to the velocity? No. So not entire part of the length, some part this is perpendicular to the velocity, of course. Some part of the length would be perpendicular, but not the entire part. In those situations, let's suppose this is end A, this is end B, we have to talk about the effective length. We have to talk about the effective length, and what is that effective length which is perpendicular to velocity, इतना अपने दिमाग में होना चाहिए। तो कैसे निकालेंगे, आपको क्या करना है, you just need to टिक 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 टिक, आपको ये जो पार्ट है ये हो गया आपका परपेंडिकुलर लेंथ, ये आपका दिस इज द इक्विवेलेंट लेंथ है ना, दिस इज द इक्विवेलेंट लेंथ which is perpendicular to the velocity। आपका ये जो लेंथ है बच्चों, let's suppose this is h height, so this is going to be your perpendicular or L effective। So in this case induced EMF, my dear kids, that's going to be BVH, that's not going to be BVL। if you write E is equals to BVL over here, assuming that this length is L, तो आपका ये गलत हो जाएगा, that's going to be the wrong thing। So the correct way of writing this is going to be this, E is equals to BVH। All good? इसको आप नोट कर लो, important है। Now let me see, can I use this concept over here or not, rather instead of doing all this thing, could I have just done this way or not, है ना। तो उसको हम फटाफट देख लेते हैं। चलो, I think that should be enough, इधर ही कर लेंगे, we have space। Now बच्चों, this is what L, this is also L। If I have L, if I have also L, and this angle of velocity is, let's suppose, theta, so this is going to be theta by 2 and this also is going to be theta by 2। So the L effective should be what? L effective should be this length, okay, yeah, this is going to be your L effective, right? Now let us see, this is your L, this should be how much? L sin theta by 2, so this part, my dear, that's going to be L times of sin theta upon 2, and when this part is going to be L times of sin theta upon 2, so the total length bachcho, that is going to be what? 2 times of L sin theta upon 2, and velocity is v, magnetic field, let's suppose that was given as B, then your induced EMF, my dear kids, should have been simply B V, this length which is 2L sin of theta by 2, polarity not a big deal, right? Standard diagram yaad hai, rightward velocity inside magnetic field, well this has to be and the positive polarity, this has to be the negative polarity. It means current should go this way. Agar isko if I try to transverse it into a battery, then definitely that should be like this. Aisa battery, equivalent battery hona chahiye. All good. So we can easily figure out the polarity of that. So when we have this random shape, आप इस कॉन्सेप्ट को यूज करो, एल इफेक्टिव का, आप इजीली आंसर ला सकते हो, कोई मुश्किल वाली बात नहीं है. कुछ भी दे दूं मैं. लेट्स से एक और एग्जांपल देख लेते हैं ना फटाफट. इफ आई टेल यू सम रैंडम एग्जांपल्स, चलो भैया हट जाओ जो 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 हाँ यू चलिए जी. सो दिस इज ऑलमोस्ट erased. Tick 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 tick. Good, we're doing good. Now let us say that, my kids, if I have something like this, if I have, let's suppose there is a probably semi ring, okay, having, let's say, center here and the radius, let's suppose that is r. Now there is a magnetic field which is present inside the field, inside the plane, sorry, there's magnetic field is inside the plane, and let's say if I'm moving it, aap isko move kar lo, let's say along this direction. I'm going to show you multiple direction. If you're moving it this way, and I just want to find the magnetic field induced EMF over here. Understand one thing, not the entire part. If it is r, then I can say that circumference should be how much? 2 pi r, since it is a semicircle, so that should be pi r. So please do not say bv pi r into r. बिल्कुल नहीं करना आपको bv, आपको pi r नहीं करना है, because not the entire region, entire length is perpendicular to the v. ना. तो क्या करना है? We're going to use the L effective concept, and this is going to be the L effective. So बच्चों over here L effective is going to be your length of AB, which is equals to 2 times of r. So the induced EMF, my dear kids, induced EMF should be BV L effective, that is going to be BV times 2R. So this is going to be your induced EMF. ठीक है. So now let's just say one more case. If the velocity of this semi ring is rightward, if I make it move rightward, then what's going to happen? What should be the induced EMF? Okay, if I go by this L effective theory, I can easily say that if when I join the end point A and B, the length which I'm going to get, वो इस तरफ होगा, that is going to be your length, and even this is moving in this direction itself. So the angle between the length and this V is going to be how much? 0, which means the induced EMF, my dear kids, that should be 0. Quite an easy way to understand. और ऐसे भी समझे हम लोग कि let's suppose it is moving towards right, इसका L effective is going to have this much, and the polarity developed, let's suppose this is O. The polarity developed between O and B should be what? Rightward, magnetic field inside, a positive होगा. It means I can replace this with a battery like this, I can replace this with a battery like this. अच्छी बात है. अब देखें, that was for the previous case, है ना. अब देखते हैं. Let us look at this part, बच्चों. Rightward, a positive होना चाहिए. It means if I only considering this length, this should be the polarity. Now you can see both will be equal in magnitude, opposite in polarity. So ultimately they should nullify and 0 होना चाहिए. एक approach तो ये हो गया. दूसरा approach, when it is moving rightward, और एक approach हो गया हमारा L effective. So you can see that V times dA times dt. It means the area swept between by this is going to be 0 only. तो आपका ये 0 हो जाएगा EMF induced when it is moving rightward. So see what is the difference? See the difference when the same ring in the same magnetic field is moved up, horizontally up and rightward, perpendicular to the AB and along the AB, it makes a lot of change. It makes a lot of difference, bachcho. You guys have to be careful. L effective has to be understood properly. So yeah, that's all for this video lesson. I'm going to see you in the next video lesson where I'm going to talk about the rotational EMF. बहुत important है. JEE has tested multiple times on that concept. So be tuned and do not forget to like, share and subscribe if you like the way I teach, bachcho. All good? Well, that means a lot. Okay? So see you guys in the next video. Till then, keep studying and keep learning. Take care. Bye everyone.